It's a pleasure to introduce Thomas. It's the first time I can introduce you. And he's going to talk about an efficient key recovery attack on SIDH. And you have 5 bonus minutes because we are 5 minutes early. So you can choose what to do with them.
Okay, thanks for the introduction. So obviously this is joint work with the person who introduced me, Wouter Kastriek. It's been almost exactly 3 months, I think, since I stood here defending my PhD in this very room. A lot has happened over the summer, as most of you know, in isogeny-based cryptography. I'll give a talk about our work on the efficient key recovery attack. A lot of follow-up things, etc., have been said about it. I'm obviously not going to talk about that and focus on how we tackled it, especially in view of how this is also some sort of workshop thing. I feel it's important that the story building up to it can actually lead to some insights into how we eventually came to the attack. Also, if people saw the Isogeny Club from Crane and Jonathan, I don't know where they are there. I've recycled a lot of the slides. Obviously, I had to condense it a bit because people know Isogenies here. But you'll see that I've recycled some stuff. But it's definitely not going to take an hour and a half this time. Okay, so the outline is pretty similar, a very, very brief recap of SIDH in a couple of slides just to get everybody on the same page. Then isogenies in dimension 2, but we're going to have some talks about that as well. And then in the end, basically the 2-dimensional isogenies will lead up to the glue and split attack in some sort of natural way, if you wish. Okay, so the SIDH recap, this is a isogeny-based protocol from 2011, if I'm not mistaken, by Joe and the Phil. Where is Luca? Sorry, I didn't see it. Yeah, 2011. Okay, so it stands for supersingular isogeny Diffie-Hellman. So we have 2 parties, Alice and Bob, who want to exchange a key in some way. You can do it in a lot of ways, but if you want to use isogeny between supersingular elliptic curves, you have to do some sort of extra thing, which eventually leads to the scheme being broken. But in essence, we have a supersingular elliptic curve over some finite fields. We have a basis of the 2 to the E torsion, a basis of the 3 to the F torsion. Alice samples some random secret kernel. Bob does the same. Alice uses 2 to the E torsion. Bob uses the 3 to the F torsion. Now the problem is, instead of just like sharing their codomain curves, which would just be EA and EB, they actually also need to share the image of the other party's torsion points, because otherwise they can't really make a commutative diagram in any way, because Alice cannot interpret GA, so her secret subgroup on EB, regardless of how she stores it, whatever. You really need this torsion point information. And if you share the torsion point information, you can actually compute 2 other isogenies, 5'A and 5'B, to then end up in, well, not the same curve, but an isomorphic curve. So we're just really interested in its J invariant, and we have a shared secret. Okay, I'm assuming everybody knows this. So the security of SIDH SIKE, like the quantum security in general, for most schemes is a little bit trickier because, well, there's some latency, some communication calls between quantum computers, etc. If you want to read about that, I don't know too much about it. Daniel Bernstein has a blog post about that I can recommend if you want to delve into that deeper. The generic attack, the best ones are the claw finding algorithm, which is slightly better in the quantum setting than it is in the classical setting. Then there's also these torsion point attacks on SIDH. I think this one is the correct. Okay, so this is from Crypto 2021 with all the authors. I think half of them are here, at least, where they already used some torsion point information to actually attack SIDH, but only if in the previous slide 2 to the E was much larger or much smaller than 3 to the F, then SIDH was already broken. And our work, assuming we know the endomorphism ring of the starting curve is heuristic polynomial time, but we need to do some pre-computation of integer factorizations, but we'll get to that in the end, why we need that. And then another thing for maybe some mathematicians who don't really know what SIKE is, I don't know everybody here. Basically, you cannot use a long-term static key in SIDH by this paper from 2016. So basically, you need some key encapsulations encapsulation mechanism, and then you get SIKE, which was or it still is a submission to the NIST post-quantum standardization process, and is now still in round 4, although obviously unless they fix it in some way that isn't really public yet, it's probably not going to get accepted. So yeah, so this is just SIKE, which was so far I think claw finding was really the only. This one has balance parameters, so the second attack does not apply to SIKE, obviously. Okay, and the only other thing I want to say more generally is the computational versus the decisional isogeny problem, which was quite important for our attack. In essence, if you want to compute an isogeny, if you want to find an isogeny of a certain prime degree, where L is typically a small prime, 2 or 3 or whatever, in case any integer, then it's equivalent in a way to having access to an oracle which can predict if something is L to the I isogenous to one another. Let's say for now for all I in between 0 and k. And how would you do that? Well, basically the same way you would actually compute an L to the k isogeny. You just start from E0, you do an L isogeny, a chain of k L isogenies concatenated. Now, assuming we have access to an oracle who can answer the second question, what we can basically say, like, okay, for our first step, we have L plus 1 options, at least in the SIDH setting, not always, but here it's L plus 1. Which of these possible E1s is L to the k minus 1 isogenous to this last one? With overwhelming probability, it's only going to be 1. Pretty much all the time, really, given cryptographic size prime fields characteristics, sorry. And then we can continue this path. Once we know E1, we can go to the next one. In SIDH, we have L options, where L is like 2 or 3. So we really need to not verify that many things. And we can just walk and reconstruct the entire chain. Now, this gives a lot more leeway as well. Obviously, let's say we can only answer this question for I equals all even numbers. You can just reconstruct E0, E2, E4, E6, and so on, because then we only need to check L squared options. This is mentioned at least in this paper. If you want to read a bit more about the computational problems, it's possibly that it's mentioned elsewhere, but at least you can read about it there. Okay, now we're going to talk about isogenies in dimension 2, unless there are urgent questions. No. Okay, so we're going to talk about isogenies in dimension 2, but then a priori you also need to talk about what objects we're working with. Isogeny-based crypto, apart from CRS and maybe some other schemes, it's typically supersingular elliptic curves that we're working with. And we're going to replace the elliptic curves by abelian surfaces. Now we're going to have to replace it by something else. It's called principally polarized abelian surfaces. And that's actually quite an important distinction, because if you don't have a principal polarization, you can't even write down an equation for it. You can't do any math with it. Ben Smith's PhD thesis deals with that a little bit. I definitely can recommend checking this out. I thought Ben Smith was going to be here, or is he going to give it tomorrow? Okay, tomorrow. And he's going to give a talk about polarizations as well, I think, which I'm quite looking forward to, because it's to me at least, not a super intuitive thing, but it's very important if you want to talk about abelian surfaces in general. Okay. Also, we want to see like what's supersingular in higher dimension. While ordinary stays ordinary, but in dimension 2, supersingular, you already have 3 options. Supersingular itself, very special or super special. If you go to higher dimensions, it's even more spread out. If you want to read why we argue that super special is the only correct notion in isogeny-based crypto, you can read about it here. One of the main reasons is that if you use super special, that's the most restrictive, and you stay over FP squared, which is a nice property. It's easy to have to not have to go to arbitrarily large extension fields and so on. So super special, like, definitely seems to be the correct notion, at least in our setting. Okay, so these abelian surfaces are typically denoted by capital A, I think, in most math literature, and they break down into 2 types of objects, in a sense. As soon as you have some sort of principal polarization, you have the products of elliptic curves, so just like a component-wise E times E prime, just as you have the plane is X and Y, basically, and a point on this surface is then a point on E and a point on E prime. But you also have the Jacobians of genus 2 curves, As you see, these genus 2 curves are given by an equation that is very similar to just the short Weierstrass equation, but a little bit more, I don't know, a little higher degree. For certain formulas, the degree can be 6 as well, which makes the formulas a lot easier. But keep in mind also, like, we have an equation here, but this also already implies we have a principal polarization, which again is important. I've shown this in the Isogeny Club as well, but I still think this is pretty cool. That's like most people know the chord and tangent method to compute a pair of the sum of a pair of points on elliptic curves, but this can be generalized to the Jacobians of hyperelliptic curves of any genus as well. So the teal line here is a genus 2 curve, and then P1 and P2 are 2 points on this hyperelliptic curve of genus 2, and these constitute one element of your Jacobian. Similarly, Q1 and Q2 constitute one element of the Jacobian. And if you want to add them, obviously you cannot draw a line through this, but you can draw a unique cubic through that. Then you have 2 new points of intersections. And again, you flip them about the x-axis and you end up with a pair of points again, R1 and R2. So P1, P2 plus Q1, Q2 ends up in R1, R2. I just want to show this because I think it's kind of a cool generalization, and it's not as hard as it sometimes can come across. At least that's how I feel. There are exceptions, of course. I mean, not every element in the Jacobian can be represented or has to be represented by a pair of points, but this is the generic setting. Okay, something maybe not super important, well, still important for our case, as the invariants in 2 dimensions. Obviously, in dimension 1 elliptic curve, you have the J invariants. If you then have a product of elliptic curves, you have a set of J invariants. Why a set? Well, E times E prime is isomorphic to E prime times E in a very obvious way. But for genus 2 curves, you need a triplet of Ihusa invariants, and this is an ordered triplet. These are 3 ordered elements in your field. And if you're looking at the supersingular elliptic curves, I think most people know that there's roughly P over 12 of them, plus some epsilon factor like 0, 1, or 2 extra, depending on P mod 12. And if we have 2 of them, then we have P over 12 options times P over 12, but we counted them twice. So given some lower order terms, the amount should be P squared over 288, right? Keeping in mind, I forgot to say that a super special abelian surface, which is a product of elliptic curves, is necessarily a product of supersingular elliptic curves. So you definitely need that as well. Now, if we're looking at the genus 2 curves, this is the amount of super special Jacobians of genus 2 curves, P cubed over 2,880. So especially if we're talking about cryptographically large P, then this is really a negligible part, right? If we were to construct some sort of isogeny graph where the nodes were abelian surfaces, you would have a very hard time even just locating one of these if you were to take something at random, because there's only a chance roughly 10 over P that you actually have a product of elliptic curves. If you want to read more about super special curves of, well, Genera 2, but also 3, Brock's PhD thesis deals about it. I think this formula is in there as well. And just to give you, like, well, Ben Smith is going to talk about that, but like assuming we're talking about abelian surfaces without principal polarizations, this number would just be 1. There's only one super special abelian surface if you don't have polarization. Everything is isomorphic, so you can't really do any applied math with it for a cryptographic purpose or anything. We really need that polarization. Okay, and then isogeny in dimension 2, obviously you have other isogenies than just ones mentioned here. You have Frobenius and whatnot. But in a way, natural extension of a cyclic N isogeny is an N isogeny. And it's an isogeny instead of now being isomorphic to Z mod N, it's isomorphic to 2 copies of Z mod N. I mean, this sort of generalizes in a natural way, but we also need this sort of weird second condition, which is that the kernel of this isogeny needs to be maximal isotropic with regards to the N-Weil pairing. So this means that all the points in the kernel need to have a trivial Weil pairing. Keep in mind these points are here again, pairs of points on elliptic curves or something, but they're points on the abelian surface. And why do we need this is actually that it's really one of, well, at least in this instance, it's the only way we can ensure that the codomain has principal polarization, right? Because if you don't have the second condition, then you're not really sure, like computationally wise, where you land on. Things can go wrong, but at the very least, you don't have a principal polarization. This condition, well, pairings are easy to compute in practice, so this, and you can construct isogenies from this, assuming you are given the n torsion of an abelian surface and so on. Okay, so there are two types of them. Well, we found isogenies now, and we know what objects we're working with. So we have two types of objects. That means we have 4 types of isogenies. The one is, well, I don't think it has a special name. These are just called generic and isogenies, I think. I don't want to talk too much about it. I think Sabrina, I don't know where she is, will give a talk, okay, about this on Friday, about the two isogenies, like an improved version of the Richelieu isogenies for pushing through points. Otherwise, I refer to Ben Smith's PhD thesis again. 3-3 isogenies are completely parametrized here by Bruin, Flynn, and Testa. Keep in mind that this is like the Richelieu isogenies is like 2 lines of equations, and this is like 2 kilobytes of equations or something. So, I mean, we still know how to evaluate them, but they're not super efficient. And as soon as you go to higher degree or composite degree, I don't think there are any like full parameterizations, and you need to use more general techniques by Poussin and Robert. I'm not sure what the state of the art there is in terms of speed, but I think for like, if you would do like B sides in dimension 2, then it would just like, it would take years to sign something, I would say. So if you want some research topic, I think that's pretty good to try and improve. But we're going to hear a talk about that in a couple of hours, I guess. Okay, so this is then called a splitting of a Jacobian. So this is called a split and n Jacobian. Sometimes if I mention a split genus 2 curve, I mean, it's Jacobian, obviously. This is a rarer occurrence just because there's not really a lot of these abelian surfaces, right? We're going to have a talk about that as well, I noticed, by Maria. Where's Maria? There. On Friday, you're going to talk about this, I'm guessing. Okay, so in the Richelieu isogeny case, it's pretty easy. It's really just a determinant of the 3 by 3 matrix. There's a lot of parameterizations going around for the 3-3 split case. This is the most complete one in the appendix because unlike Kuhn, they cover all the exceptions like J invariant 0 and 1728 as well. What the most general setting, I think, mathematically is this. This paper, I would say, is quite short, so I think it's a nice read, but I think Martin Djukanovic's PhD thesis also deals about that in a more computational way. I can look up the title, I forgot to mention it here, but it's his PhD thesis of Djukanovic, so pretty easy to look up, I think. Okay, so these are, well, you're starting from a Jacobian, so these are sort of okay. If you look at an isogeny graph, I would say, in terms of how often they occur. And then we have, well, we start from a product of elliptic curves as a domain. And then we have these 2 options, right? And what we expect is, there's no surprises. Both options exist, by the way. What we expect is that we have more of these than we do of these, right? Because there's just a lot more Jacobians. So we expect the codomain. I mean, if nothing fancy is happening, we expect it to be a Jacobian, right? This is, well, obviously, if you look at it from an isogeny point of view, this is the dual of the splitting of an isogenies, and this is called the gluing elliptic curves along their n torsion. I like the names. And this is, I don't know, I think this is just called an isogeny between products of elliptic curves. Okay, but even though that this is a very rare occurrence, I think most people can easily write up examples of it in the following sense, that if you just take phi1 to be a cyclic n-isogeny, and if you take phi2 to be a cyclic n-isogeny, you can just like make the direct product as a 2-dimensional isogeny, and you have a domain and a codomain. That's a product of elliptic curves. It's a very boring example in a way, but it's easy to construct and at least shows that they exist. And why does this work? You can check that the kernel is maximal isotropic with regards to the n-while pairing, because the n-while pairing on this is simply the product of the separate n-while pairings. So it's easy to verify that this is well defined and behaves as expected. This kernel can also be written as this. You have an n torsion point on E1 that generates phi1 kernel, and Q generates the kernel of phi2. And this is called a diagonal kernel, because if you make it in a matrix form, obviously you have, well, the only non-trivial elements are on the diagonal, hence the name. Okay, and then the question is, okay, what happens when you have non-diagonal kernels? Obviously, you can also have that. In this case, the kernel looks like this always, where P1, Q1 is a basis for the n torsion of E1, and P2, Q2 is a basis for the n torsion of E2. Now we expect that A prime to be almost always a Jacobian of genus 2 curve, right? Except for like the special case that we talked about earlier. So the question is really like, when is this not the Jacobian of a genus 2 curve is maybe an easier question to answer, because it's more rare. And in the case of super special abelian surfaces, we only really expect is A prime to be a product of elliptic curves with like probability 10 over P roughly. So that's unlikely to ever happen, really, if you would take that at random in a graph of cryptographic size. Even when we were writing about the hash function with Wouter and Ben Smith, even if you tested 1 million hashes, that just never occurred by chance, unless you started from a product of elliptic curves or close to it. But in general, you shouldn't expect this. But when you can expect it is, well, in the natural way, if you look at the conditions under which this occurs, you can actually like attack SIDH within that settings. And because we're talking about gluing and splitting of Jacobians and elliptic curves, we try to call this the glue and split attack. So first, some examples, like when does the gluing fail? When do we not end up in a Jacobian but in a product of elliptic curves? So these first two examples are, I've seen them mentioned in multiple papers already. So if you try to compute a non-diagonal, well, an isogeny with non-diagonal kernel, which is a 2-2 isogeny, then you can only end up in a product of elliptic curves again if E1 and E prime are isomorphic, which is quite a restrictive condition, right? Similarly, for a 3-3 isogeny, this can only happen if E1 and E2 are 2 isogenous. And I specifically mention can fail because that's not a sufficient condition. You still need some extra conditions, so it's even more rare than I'm really trying to picture here. But people who are like thinking about isogenies maybe think like, okay, well, an isomorphism, that's really a 1 isogeny. So if 2-2 fails if it's 1 isogenous and 3-3 fails if it's 2 isogenous, then you can just, well, that should generalize, right? That's at least what you can think. But even if you stick to primes, it's not true. For 5-5, you already have the option that it can fail for 4 or 6 isogenies. If you go further, 7-7 isogeny, more and more stuff gets added, so it's not as simple. And only in these two specific things, it's in a way rather easy to like prove this relative to Kani's theorem. These two, if you would try and prove it by hand, I've seen it mentioned in a couple of papers, especially the ones that I referenced for the 2-2 gluing or the 3-3, the 2-2 splitting and the 3-3 splitting. They almost always mention why and how this can fail. Okay, so like the more general setting, obviously you want to talk about composite n as well, and then it's Kani's theorem, but a highly informal version because I think it's more important to give the intuition. The math can be seen in Kani's paper or our ePrint paper. So basically, an isogeny starting from a product of elliptic curves has again a codomain product of elliptic curve if it comes from an isogeny diamond configuration. What's an isogeny diamond configuration? That's the term I think he defined himself. I don't think it's in anywhere else in the literature. So basically, you need three objects. You need an isogeny itself, and then two subgroups of the kernel of the isogeny, and they need to satisfy certain conditions. They need to intersect trivially, their degree needs, the order of the subgroups need to multiply to the degree of the isogeny, and then you have the order of the isogeny diamond configuration is the sum of the order of these subgroups. Okay, so this is a technical definition. And then like the term it comes from is basically, well, the kernel of this n isogeny is of the form, well, P and Q have to be like a basis for the n torsion of E, and then you push them through the isogeny psi, and then to make the, then you pick some X and Z to make the while pairing correct for the maximal isotropicness, and then you have like product of elliptic curves as codomain again. And notice that this is an if and only if, so Kani really managed to, like 25 years ago already, apparently managed to completely determine when this non-diagonal kernel would lead to a product of elliptic curves. Okay, and we're going to try to like fill this in, this definition, because from this definition, Kani's theorem follows. So we're going to try and apply it to SIDH. Now, recall in the SIDH setting, we have access to this. And by this, I already assume that we're going to attack Bob's secret key for the reason that 2 lines of equations are shorter than 2 kilobytes of equations, but you could attack the other side as well if you want. So if you're an eavesdropper, you have access to obviously the public information, E and Alice's 2 to the E torsion basis, as well as Bob's EB and the action of his isogeny on Alice's 2 to the E torsion basis. And we want to find this, right? This is an isogeny of degree 3 to the F, okay? So this is the thing we're after. And as I said before, we will consider the decisional version of the problem, where we're just going to try and recompute the entire isogeny chain from Bob. So F steps of isogenies of degree 3. So in essence, like the first step, or at least the step we're most interested in, is well, there are 4 options for E1. Which one of these is correct? And we remark that we can easily push PA and QA through easily as well, because there's only 4 options, but this is just pushing the Alice distortion along as well, just as Bob actually did in his isogeny computation. So there are 4 options, and you can maybe already see it a little bit like we have 2 elliptic curves here, or E1 and EB maybe. How can we force this into an isogeny diamond configuration? And then into Kani's theorem as well, obviously. Well, the first thing is, as I said before, we're attacking Bob's side because the order, we sort of want to minimize the dimension 2 isogeny computations. So the capital N in the isogeny diamond configuration is its order, which translates to an n isogeny. So we want to keep this n small. So that's why we attack Bob's side, because it's a lot easier to compute chains of 2 isogenies. Well, a lot. Okay. Reasonably faster. So then we would already need to replace this n by 2 to the E and also here, right? Now the first obvious choice would be, oh, okay, what if we simply replace psi with phi1, which we take as the last part of Bob's isogeny chain. So just the last, well, I think like an isogeny of degree 3 to the F minus 1, right? So everything except the first step in Bob's isogeny computation. What happens then? Well, the problem is here then that all the subgroups of the kernel would need to be some power of 3, right? So that's a bit annoying because then, well, 2 is not divisible by 3. So you would need to have 2 to some power equals 3 to some power plus 1. If you try to attack Alice's key, it would be 3 to some power equals 2 to some power plus 1. The highest values you can enter here is 9 is 8 plus 1. So from a cryptographic point of view, you're sort of stuck here. But obviously, like the problem is that you only have option, like you can only add 1 here. There are no real prime powers that differ by 1 in this sense, at least not in this setting. Okay, so we're going to have to adjust it a little bit, and we're going to construct an isogeny gamma, say, of degree C. And this degree will be this number specifically. It'll be clear why. Well, actually, it's already clear why, right? If we replace the order of G2 simply by 2 to the E minus 3 to the F minus 1, then this equation is trivially, the fifth one is trivially correct, right? So we're going to see if we can enforce this. Now let's assume that we can construct an isogeny of this degree. And the first question is this positive? Is a good question. Especially in the SIKE settings, this was not always positive, at least. For the larger parameters, I think 3 to the f minus 6 was the last non-positive one. So this is definitely not always true. I'll talk about how you can circumvent this, but if this is not positive, you can attack Alice's side, obviously, because then you have 3 to the f minus 2 to the e minus 1, which is definitely positive. So this is not a hindrance or of any kind. Second question is, how can you compute this? Because, well, C may be a huge, large prime that you cannot computationally or even store in polynomial time, but that you need to have an exponential amount of computing power, but we'll talk about that later as well. But just assume now that we can do this. Okay, how can we fix this isogeny diamond configuration then? Well, we're going to take the dual of gamma and then concatenate it with phi 1, which recall was the last part of Bob's secret isogeny. And this concatenation will be our psi in the isogeny diamond configuration, where G1 will be the kernel of the dual of gamma. Recall now that we have an isogeny from C to EB, where we sort of pass through E1. G1 is the kernel of dual of gamma, and then G2 is the gamma of Bob's secret kernel that we pushed to C, of course. Now these have co-prime degrees, so obviously they trivially intersect. And then the total degree of psi is obviously 3 to the f minus 1 and that times C, which is written out in full here again. 2 to the e minus 3 to the f minus 1. But this doesn't matter because this is part of what Bob already computed. And this is, well, we assumed for now that we can compute this, okay? And as said before, the main reason why you even take this C is basically to make this fifth condition work, because obviously this is always true. And in the SIDH setting, you don't really have access to a lot of other information either, right? Okay, and what now? Well, the only thing that we really need to do is we finish the attack. We consider the product of elliptic curve C times EB, where like if you compute an isogeny from C to EB, at least in our setting, we sort of pass through E1. I've written down PA comma 1 here because, well, it's just PA that we pushed through from E0 to E1. We're not really working with PA anymore. We are considering the first step in Bob's isogeny chain, but that's easy to do. And if you then check this kernel, so we take Alice's 2 to the E torsion from E1 to C, and we also take it to EB. Same here with the other basis generator. Then in practice, all it takes is to compute this isogeny, which is a 2 to the E, 2 to the E isogeny. As follows, it's just a chain of 2 isogenies. This is just a gluing. Generically, these are just Richelieu isogenies. And then the last question is, well, what's A prime? Remember, we had 4 options for E1. And the thing is now, if we end up with E prime being a product of elliptic curves, then our setting was correct. And the degree of, well, the degree that we actually used from E1 to EB was actually degree 3 to the f minus 1. In all the other cases, it will not have been 3 to the f minus 1. Well, with overwhelming probability, you never know, but in cryptographically large size, it's negligible and that it can happen by chance to be also true. But in practice, if you end up with a product of elliptic curves, you basically know, okay, we have found the correct first step of Bob's secret isogeny. And then you can recompute the entire thing over and over for E2, E3, and so on up until the very end, basically. Then one very non-minor detail, actually, like how do we even, I see Lauren's like, yeah, how do we even compute this? Because this is obviously not a trivial thing to do, because 2 to the E minus 3 to the f minus 1, but we kind of want as many i's here as possible because we want to reconstruct the entire chain, right? how do we compute this? Well, in the SIKE setting and in general, you cannot hash into the supersingular elliptic curve set without knowing its endomorphism ring. So knowing the endomorphism ring allows us to actually use C, so the codomain of this isogeny, to be equivalent to EI, which makes things a lot easier. So especially like this is popular elliptic curve, supersingular elliptic curve to start from. They didn't use that in SIKE. But this has an endomorphism with a very small degree. And if this C can be written as the sum of two squares, and then you can factor it like this, where U and V have to be interpreted as scalar multiples. And then I can be replaced by this endomorphism iota, and this computing this endomorphism of degree C is very easy. So like in number theory, this when does this happen? First of all, to check if this is possible, you need to factor C. At least I don't think there are any ways to know if this is possible without factoring C. So you need some sort of pre-computable factorizations. But it's even for the largest SIKE parameters, the largest one was like a couple of hours that Magma took, I think. So this was not really an issue. And this can be written as a sum of two squares if and only if all its prime factors, which are 3 mod 4, have an even exponent, I think. So this is not always the case. You can definitely not expect it to always work, but I'll talk a bit on the next slide how you can sort of give yourself a little bit more leeway as well. And what they did in SIKE is they used this starting curve, which is a 2 isogeny away from this one. So unsurprisingly, it has a similar endomorphism where you can use a very similar trick, right? So if you have knowledge of the endomorphism ring, you can do a lot more, and you can translate this endomorphism along your walk and Bob's graph. But even in general, if you would just know it's endomorphism ring, if you have this other small endomorphism, that's okay too, but you can use the KLPT algorithm to create an endomorphism as you wish. We focused on SIKE, so unless Wouter implement this last one, I don't think so. We don't know what the bottleneck here would be, but we don't expect it to be much. So if you know the endomorphism ring, you can recover the secret key in the SIDH protocol. Now, the other question obviously is, what if we don't know? Well, you can sort of do a Hail Mary and hope that this number is smooth in some way. But obviously, like, this is almost never going to be true, especially because E is a couple of hundred for most SIKE parameters, and there is no real way to do a degree C isogeny. One of the reasons also is, even though you have like Philly square root, which was an asymptotic improvement, you still need to work over huge extension fields. I think Lorenz may be talking about that tomorrow. No, okay. But still, like most algebra software packages struggle really hard with huge extension fields. So even if you can get C a little bit smooth, I think it's shaky at best. But there are some other ways to add more leeway. As said before, well, we don't really need all the i's in between, right? If you can just find E10, that's fine as well. Then you need to check 3 to the 10th options, but cryptographically, that's still a trivial amount of work. Again, this also allows us to like not have to worry about that this is larger than 0. You can just start with C equals 2 to the E minus 3 to the F minus 7 was in the largest SIKE parameters, I think, that we had to start. 6, okay. Then you need to check a lot more options, and obviously. And the thing is, also, if you know the action of Bob's isogeny onto the 2 to the E torsion, you also have it on the 2 to the E minus J torsion, obviously, just multiplied by 2 to the J. And this allows us to actually, like, with a known endomorphism as well, to allow us to find, once you're further up in your attack and once you're at like E20 or something, you have a lot more leeway to find the C for which almost all or all prime factors are 1 mod 4, which allows us to do the Gaussian integer trick. Well, sometimes we had like a 3 mod 4 with a square exponent, but that happens rarely. So really you want this to be to factor into primes 1 mod 4. And then finally, like, well, C may live over large extension fields. Well, the C torsion may live over large extension fields, but nothing is really stopping us from extending Bob's secret isogeny as well. Because if we're going over extension fields anyway, we can like try and add a D prime there to like make C smoother. As long as D prime is not less smooth than C, we win, obviously. The problem here is also, well, if you add a factor D prime here, then this will become negative rather quickly. Especially the first steps in the attack are the hardest, so you don't really have a lot of leeway. Okay, now you may think that this adds a lot of leeway, this factor D here, which it does, but it's also by far the most annoying factor, I would say, because at that point you're just guessing. You're just like, okay, we're doing a walk of 2 to the E minus J, 2 to the E minus J. We end up in a Jacobian of a genus 2 curve, and then you look, okay, is there any of my DD isogenous neighbors, which is a product of elliptic curves? There's about D cubed of those, if D is prime, and you can have very clear formulas for the composite numbers as well. But again, that the fact that any of them would be a product of elliptic curves is again like D cubed over P. So the numerator will never be even close to the denominator here. So this will not happen by chance. Problem is that, okay, this looks like a very attractive, like, okay, we can really use this D to make this positive and just make this as smooth as possible. But the problem is you need to compute D cubed neighbors roughly. The DD isogenies by Cossin and Robert are not efficient. And moreover, they live over extension fields of expected degree D as well, over a field of cryptographic size. So computing this is, I think we never tested it, but I think it's in practice, it's easy to describe in theory, but in practice, I'm not sure how far you can push this. But again, actually, we're only looking for an oracle that says if one of them splits, so maybe on Friday morning, we will hear if this is actually easily computable for large D, because checking if something splits is a different question, of course, than computing all the DD isogenous neighbors. But again, this should, in theory, work because the chance of it happening at random is really 0. Okay, and that was my talk. Thank you for listening.
Hello. So we have quite some time for questions. Are there any questions from the audience? Yes, please.
Yeah, so for the Zoom audience, if we want to check if the image abelian surface is a product of 2 elliptic curves, is that easy to check?
What's the input?
What you compute here?
A Jacobian and okay, do you want a Jacobian with a given kernel, see if it splits, or Jacobian, does any of the DD neighbors split?
No, just if you go back like to slide 12 or so.
Okay. I like PowerPoint, but this is annoying. Okay, so just a general NN splitting case. I think we're going to talk about. We're going to have a talk about it by Maria on. Okay, this is really lagging a lot, so we've definitely paused it. Okay. Not yet here then.
Yeah, a bit further, I think. Sorry.
So this one.
Well, assuming the next slide, I think, if you have this map, the point is that you compute one of these maps, right? And then in the end, you check if the codomain you get is actually a Jacobian or product.
In the 2-2 case, that's just a variable small delta in the Richelieu isogeny computation, that's 0. In the 3-3 case, oh, I didn't write that. Or did I say that? In the 3-3 case, it's a capital delta of this formulas, which is 0 that completely determines the splitting. And for more general work, the way that Kuhn does it is that he projects the genus 2 curve C on the Kummer line and does the same with E1 and E2. And then he just checks if there is a morphism of the correct degree between the Kummer lines. and then lifts it again to the Jacobian. Is it easy? I think Martin Djukanovic PhD thesis goes about that in a computational way, but I don't know how much we'll be talking about that on Friday. But it's some sort of Gröbner basis computation with each like 3n/2 variables already, so it scales kind of bad. I feel maybe there's some improvements to be made there, but just checking if something n splits seems to be. I mean, it's hard to tell. I think computing all the neighbors in general is a lot harder question to answer than it is to just check if something n splits. This is slightly easier, mainly because if you actually go to the Kammer line, you don't even need to define a kernel. You're really looking just to map the projective line to another projective line. So you can avoid all extension fields as far as I'm aware. So this should be a computationally easier problem because the kernel, we're not really interested. It may be defined implicitly. So I think, I mean, yeah, I hope to learn more about it Friday morning.
Thanks.
Okay, thanks. So the microphone was not connected to Zoom, but at least we gave the impression of a good technical setup. Yeah. So are there other questions? Yes. Maybe it's then better you ask the question and then Thomas repeats the question.
Okay.
Yeah. You can do it? You can hear it? Okay, then it's better. Yeah.
Okay, can you go back to the end now?
I'll try not to click too
Maybe
quick.
once those eyes appear. So
Yeah,
maybe for a little bit to the. Yeah, so maybe we can stop here. Maybe so do you really need? So in the end, you have these 2 to the e minus 3 to the f minus I for every single step where you do this decisional oracle, but you have like a stronger decisional oracle, right, which checks whether there is a correct isogeny with the correct action on the torsion. So isn't actually enough for this to have this C for 2 to the e minus 3 to the f for that to be whatever evaluatable, and then just run like a GPST attack.
Yeah, where you like push the points through.
Yes.
Yeah,
and then
you can do that as well. Yeah.
And then avoid, because here you need this C to be nice for every single I.
And
right?
if you just have one,
But you just need
if
it
you
for,
have
like,
one
just-
large enough, you can like move your chain up a bit, I guess. Yeah. Yeah, that's possible as well. But we didn't, I mean, it was not implemented like that for us. But if you have access to one large enough, so like if you have this one, then that's enough to attack the entire chain. Yeah, that's another thing that you need to take into account.
okay.
Also, alternatively, but Wouter is here, so alternatively, I think that was suggested by Luca De Feo that you can just start from the other side, right? That was your suggestion. Basically, instead of moving up the chain, if you have an endomorphism of E0, it makes more sense to try and compute a dual isogeny and like try to find EF minus 1 first. There's also 4 options there, and then et cetera, et cetera. Then you don't have to move this endomorphism through your entire isogeny chain as well. So that makes more sense, I guess. So there are some tweaks possible there. I mean, the hardest part of the oracle is indeed finding the longest chain. And then you're done.
Okay, thanks, Chloe.
I have 2 questions. On slide 15, sorry.
That's close.
It's not too far. I thought now's the time. Yeah, so you gave this example. I don't quite understand this product isogeny. So what does it, so with what does it do to the second part of the product, for example?
You have an isogeny from E1 product with E2 to E prime 1 product E2 prime. So this is really like, I don't know, component wise, like joining two cyclic n-isogenies, and that's it really. If you have a point PQ here, then you just have to compute phi1 of P and phi2 of Q, and you're done. That's the only thing that's going on, really.
But don't the zeros make it not finite kernel? Or not?
This is the kernel, right? It's just
Okay.
the kernel of this, and then with the
I guess
finite and fixed.
I guess I'm trying to I'm trying to put it in an isogeny diamond in my head and failing. That's the
Okay.
we can also talk about it later.
Yeah. Okay. I'm thinking now. That should also work in an isogeny diamond, right? Yeah, I don't know immediately how to put it in an isogeny diamond either. So
Okay, we can discuss it later. Okay, and the other question, I won't make you go to the end again. So right at the end, you said if we're looking at the generic case, so we have unknown endomorphism ring, then you want to have this D and this D prime to help you with the brute force, and you might not need to compute DD isogenies because you can just check the splitting, right? This is the other question over there. But is that only if D is small then, so that you can really just do a whole D in one go? Because if you need to factor it into smaller steps.
Oh, if D is not prime, I think, but I'm not sure that splitting is harder because the splitting criterion, at least by Kuhn and most of the things, really only deal with like prime D. So if D would be composite, then I think your best bet is to just compute the smallest prime factor isogenies, to like make a set of those and then check if one of them splits there.
Okay, so in your method for that case, you're really looking for small prime D.
I think prime, not necessarily. I mean, if D is like, I would say like, let's say 35, then you could still work over an extension field.
Sure.
And then use the 5-5 isogeny should be okay to compute, and then check if one of those 7-7 splits then.
But you're looking for it small.
Yeah, I'm not sure computationally, we never tried it. I don't think the state of the art is substantial in the literature for that. But yeah, D small has to be like almost really, really small, I feel. I think also one of the bottlenecks would really be that like both Magma and SIDH and whatnot really struggle with high degree extension fields in general. So I don't know. I don't feel like we can really push this too high. I think if we're talking like D1000, then yeah, it's not going to happen. I don't know.
Sure, but I mean, you don't just want it smooth, right? You also want it small for your.
Yeah. Oh yeah. Sorry, if that was the question, then D smooth.
That wasn't clear,
Well, that's actually a good question. If D is smooth, like let's say 5�7, then you just have this D cube to be really large, though.
But then you're really
the computations are easier, but you need more like parallel processors. I mean, it's easier from a parallel processing point of view, I guess. Yeah, that's possible.
Thank you.
Thank you. Let's check the time. In the meantime, if you want to ask a question, this is the no, you don't have time. Okay, so let's thank Thomas again, and let's move to the next speaker.